Good afternoon and welcome to today's seminar, Convergence and Contact in Abaqus Standard. I'm your host, Kelly Peebles, and joining us today is Randy Marlowe, Senior Expert Solution Consultant for Dassault Systems Samoa. And now I'd like to introduce your presenter today. Randy Marlowe is a Senior Expert Solution Consultant in the Dassault Systems Samoa office in Dearborn, Michigan. He has MS and PhD degrees in Theoretical and Applied Mechanics from the University of Illinois, Urbana, and 25 years of experience with Abaqus. He has been using Abaqus Explicit since its first release in the 1990s. Please welcome Randy Marlowe.
All right. Hello, everyone. This is Randy, and I'm coming to you from my office in Dearborn. And a little correction there. This is a seminar on Abaqus Standard, of course, and I've been using Abaqus Standard even longer than Abaqus Explicit, so that last bullet item was left over from the last presentation I did on Abaqus Explicit, but we're going to be doing Abaqus Standard today, so no big deal there. So what is Abaqus Standard? Abaqus Standard is a general purpose implicit finite element solver code. Runs into batch mode, so it's not interesting to look at. Of course, it's a very powerful piece of software for generating finite element solutions. Dates back to the early 1980s to the old HKS company. It does general nonlinear static simulations, general nonlinear dynamic simulations. It can do linear dynamics and completely linear static simulations, and it can do heat transfer and acoustics, and it can do a lot of stuff. Today we're primarily interested in this general nonlinear static simulations and or the dynamic simulations. So not anything on the linear simulations today. All right. So here, just to get started, is an example of an Abaqus Standard nonlinear simulation involving contact. So and it also has issues with convergence. So this is a really good example for today. And I'm trying to pull this highly flexible rubber disc through this rigid ring, which has an elliptical cross-section. For some reason, I built this example problem as an exercise in our 3D experience platform. And what you see here is animations from Abaqus Viewer. And it gets only so far, and then it grinds to a halt. So this is a contact model, so is there an issue with the contact? Well, not exactly, not at this point. So what do we do? Well, we can go look at the Abaqus message file to see what was going on in the numerical calculation, and we see interesting messages about negative eigenvalues, solution is diverging, but it looks like the contact is okay. You can see contact constraints are converged, which sounds good, whatever that means. So, perhaps this is not a contact issue. If we look at the animation, we can see that, this disk is wrinkling up, and so maybe I'm just not able to find static equilibrium. And that's really what is happening here. It's not too sensical, really, to do a simulation like this, which is quasi-static, without taking some special considerations if you're using a completely static procedure. So I went to a completely dynamic procedure, and I was able to pull this disk through that ring, and you can see it flop around like this. This is a dynamic simulation. So I overcame the lack of static equilibrium by simply looking for dynamic equilibrium, and I didn't really show an intermediate result where this disk got partway through and then kind of got stuck, and that was because the edges of the disk were dragging along the surface of the ring, and I had a contact pair which can have difficulties with edge-to-face contact. So I switched to the general contact, which we'll talk about today, and I was fairly easily able to complete the solution. Looks sort of like somebody throwing up a pizza crust, kind of, but interesting. So let's talk about this idea of equilibrium. So we see here on this slide a simple expression of equilibrium. Applied loads equal internal loads, basically, although the terms are written on the same side of the equation this way, so the applied loads minus the internal loads equals 0. So we have balance. We have static equilibrium in this example here. Now, how do we solve this equation? It involves, in general, the degrees of freedom of the structure. It can involve time. It can involve the velocities. A lot of things. So how do we solve this equation? Well, you can imagine different ways, but Abaqus Standard uses a technique called the Newton-Raphson method. Now, the Newton-Raphson method is a process of incrementation, iteration to reduce the nonlinear equation to a series of linear equations. And I'm going to show an example of how this is done rather than showing some slides with some flow charts or something. I'm going to actually do an example. And it's a rather simple example, so we'll start out here at the top. And basically this example is finding the square root of 2 using the Abaqus solution method and writing it in a form which is analogous to what Abaqus does in a structural analysis. And so my solution variable is called x, and my internal force, if you will, is just simply x squared. My applied load is some value p, which of course we're going to set to 2 eventually. And the first thing we have to come up with is a known starting point. Now, in a structural analysis like Abaqus Standard solves, it's very well known that you would start from the base state. If you have an undeformed model or a model with no loads yet, then that would be the initial state. And then if you run some load steps, then the base state for step 2, say, is the state at the end of step 1. But whatever we're doing, we know a solution. So whether it's just a trivial solution, or in this case, the known solution is x equals 1 when p equals 1. So we have a known load, if you will, 1, and a known solution 1, and that solves our equation. In this case, it solves it exactly, but that won't always be the case unless you're talking about 0 equals 0, say. So we will start with the known solution, x0 equals 1. You can see that here. Now, we have to come up with some method to get to the square root of 2, and we don't want to cheat and use our calculator or look this up in a book. So we're going to do an increment to the known solution. We'll call that delta x1, and we're going to do a increment of load. We'll call that delta p. Of course, x0 and p0 are both 1 in this example, but I'm writing it this way on purpose so you can see the analogy to what Abaqus is doing. And now we have to have some way to solve for delta x1. Now, we could take the square root of both sides, but that's cheating, so we're going to linearize this equation. And so we do that in this simple example. We'll simply square it out and throw away this higher order term here, delta x1 squared, as being small somehow. And of course, x0 squared is equal to p0, or 1 minus 1 equals 0, if you will. And what is left behind is a linear equation for the correction delta x1. So as long as x0 is not 0, we can divide by 2 times x0 and we can find delta x1. So we have a solution process for our linearized equation. And so this is what Abaqus Standard does. It linearizes the structure and solves for a load, a solution increment corresponding to the load increment. Of course, for a system with many variables, it's not so easy to do this as it is here. We can just divide by 2x0 to get our correction, delta x1. So that's where the big time solver comes in Abaqus Standard, and where all the computer power goes when you're running Abaqus Standard. A lot of it goes into running this, what turns out to be a large matrix solve at that point when you're looking for these corrections to the solution. So let's go ahead and plug in some numbers. Let's try a load increment of 0.1, calculate our correction, which is also equal to the increment for the first iteration here. And we put in the numbers and we get 0.05. So we've done that process, and now we have the next important thing. We update our solution by adding on the correction, or the increment in this case, to get 1.05. That is our current estimate of the solution of x squared equals 1.1, basically. So how do we know if that is a good solution or not? We have to check to see how close we are to 0 if we write both of those terms on the same side. So we would have 1.1 minus 1.05 squared, or the other way around. In any case, the little bit that's left over is referred to as a residual, and in this case it has a magnitude of 0.0025. And now we come to the next important thing about the Abaqus standard solution process, and that is what do we do with this result? Is this a good result? Is this what we want, or not? So we have to have some way of deciding if our process is close enough to our required solution or not. And in this case, let's just say that it's not, and so we'll repeat this whole process again by replacing the original 1 with the 1.05, and we'll do this linearization again, and so we have to pass through the solve process again. We'll call that a solver pass, and we get another correction, which now is negative, but it's much smaller than the one we had before, which was 0.05, and so we add on the next correction, and we get a new estimate of the solution to x squared equals 1.1. We get 1.04880952. That's to 8 decimal places, I think. And at this point, I got tired and cheated, took out my calculator and calculated square root of 1 to the same number of decimal places, and you can see it's very close. The residual, if you will, is very small. So our process has produced an approximate solution to the first load increment. That is, we have an approximate value for the square root of 1.1 in this example. And so we can go on to the next load increment and repeat the whole process and get an approximate value for the square root of 1.2. And so on and so forth. Eventually, we can arrive at an approximate result for the square root of 2. So in this process, we have increments, iterations, and we have checking. And this is the Abaqus standard solution process. It's just the old Newton's method written in this kind of format. All right, so we saw that we have a residual tolerance check, and it's really a ratio check. You can see the equation here for the residual, the maximum residual at any degree of freedom in the set of equations has to be less than 0.005 times this mysterious Q tilde, which is simply a running time average of a typical force in the mesh. You could divide by Q tilde, it wouldn't be 0, and so you really have a ratio check. And that ratio, R max over Q tilde, is less than 0.005. This number, 0.005, is somewhat arbitrary. It represents a reasonable trade-off between accuracy and efficiency, and it's what's sufficient for most cases. It is a user-definable parameter. If you want to go around changing these things, it is possible to do that. All right, so there is a idea in Abaqus that because we're using ratio checks, then Q tilde adapts this time average force adapts itself to the model, and so because we're doing a ratio, then we get a relative residual check. So the same code that works for a small cardiac stent works for a concrete arch dam. All right, and then we have another check. Abaqus checks the corrections themselves, and the idea is that the corrections should get smaller and smaller, which is what you would expect if you're approaching some state. So the corrections need to be getting smaller and smaller. In our example, this is indeed what was happening. We went from 0.05 to 0.000 something, whatever, 0.0011948, and so it's getting smaller and smaller. If you kept doing this Newton's method for the square root of 2, this thing would become as small as you would like. You could get as close as you want to a number which, when squared, would give you 2. All right, so those are the two checks. Again, just like for the force residuals or the moment residual or whatever, the the ratio of the correction to the increment in the solution itself is this has to be less than this 0.01, which is a user definable parameter, and you can see that on this slide. All right, so that's the basics of the Abaqus standard solution method. It's not complicated in concept, but of course in practice it's very complicated to write down, say, the tangent stiffness for a large structure with contact and nonlinear material properties and all kinds of things. It's very numerically difficult to do that. Fortunately, Abaqus is programmed to do that, so we can focus on building the models. One thing that goes into a lot of nonlinear simulations in Abaqus standard is contact. So let me talk about contact a little bit. And I want to talk about three basic features of the contact in Abaqus standard. There's the idea of contact discretization, constraint enforcement, and contact tracking. So what we see here in this picture is an example of a shell contact model. And I worked on this model many years ago when the Abaqus standard contact definitions are much cruder than they are today. And it was quite a challenge to account for the shell thickness and the stacked sheet metal. And of course, all of these problems have gone away more or less with the today's algorithm, say in the general contact definitions that you can put into Abaqus standard. You don't have to worry about enforcing the thickness of the shells and things like that. It just is a straightforward definition. You can even try defining contact without any mention of actual surfaces by name in a model like this today in Abaqus standard. All right, so let's talk about contact discretization. Where is the contact constraint applied? Abaqus standard has two contact discretizations. There's a node to surface and a surface to surface. Surface to surface is in red here because I want to highlight that as being the recommended contact discretization today in Abaqus standard. Node to surface is a point constraint. We'll see that in a minute. There's a surface to surface is a more elaborate smeared average type constraint. We have constraint enforcement that we need to define, and we have two main kinds of constraint enforcement. There's a direct method achieved with adding extra variables to the model called Lagrange multipliers. If you're interested in this idea of Lagrange multipliers, then you can look at the simple classical problems from calculus of variations. It goes into the discussion of Lagrange multipliers, or you can use a penalty method. Again, penalty method is in red because I want to highlight that as being the recommended constraint enforcement. And then we have contact tracking. How does the constraint evolve? Do we have algorithms that can track arbitrary relative motion between the surfaces, or are we using an algorithm which is really only useful if there is a limited situation where the surfaces are close together, come directly together more or less, and then do not slide around a lot relative to each other, where a lot is relative to how big the elements are on the contacting surfaces. So finite sliding is in red because that is the algorithm which would tend to work in every case, whereas small sliding would fail miserably if you tried to use it in a finite sliding application. Okay. So the contact discretization, we have the node to surface, which is the default for contact pairs. It's not available for general contact. And we have the surface to surface, which is what's inside general contact. It's also recommended now for the contact pairs. If you're a big fan of contact pairs, you can use the type equals surface to surface option to get this algorithm for the contact discretization. This is a more sophisticated constraint, which considers both the surfaces, the master and the slave, And it has a more sophisticated constraint, which is enforced in some sort of mathematical averaged way on the slave surface. All right, so you can see a picture here of the what is going on there. So the contact is more involved constraint, and I've heard people refer to a method called the mortar method in reference to this type of surface-to-surface constraint. I don't know exactly what's programmed into Abaqus. Even if I did, probably wouldn't be allowed to say, because a lot of development cycles went into getting the contact to be the way it is today, and we don't want to give away our tricks, I guess. But suffice it to say that contact is enforced in some sort of average sense. And additionally, if you go to general contact in Abaqus standard, which is probably what you would want to be doing today in Abaqus, you get access to the algorithms for edge to face, edge to edge, vertex to edge, which can greatly enhance the robustness of the contact model. So it was the edge to face contact in the general contact that allowed me to pull that disc through the ring, because the edges of the disc were sliding along the faces of the ring, and in just a simple contact pair definition, it was having trouble maintaining the constraint with only face-to-face contact. Okay. So here are some more one more advantage of the surface-to-surface over node-to-surface. We have an enhanced ability to compute the contact stress itself. So in this example, we have a sphere which is pushing against a large elastic body in a local region there in the side, that little red ellipse, you can see it there. So the contact is, isolated in this small area here. This kind of model, or this kind of situation, has an analytical solution from the theory of linear elasticity, and you can calculate that. And you can see that the surface-to-surface algorithm is very accurate, and it's also producing a nearly axisymmetric stress distribution for the contact pressure, which is what you would expect. The node-to-surface is kind of ragged looking, and not nearly as nice as the surface-to-surface. All right, so just a summary of surface-to-surface versus node-to-surface, and you can get the recording for this and pause it here and take a screenshot of it or whatever. You can have that. And if you read through here, you would see the differences between surface-to-surface and node-to-surface, and you might come to the conclusion that, yeah, this is surface-to-surface is what I want to be using. And as I said earlier, you can get access to this algorithm through the general contact framework, which is what I would recommend today in Abaqus standard. The contact enforcement method is the the way the constraint is maintained, if you will. We have that direct enforcement method, and we have a penalty method. And down here at the bottom, you can see this little XY plot. If the H is negative along the horizontal axis, then we have no pressure because H is the penetration. Penetration is negative. We have a gap. And when we get to zero penetration, then this Lagrange multiplier of the direct enforcement keeps H at zero at most, and so we get a very nice constraint. However, it's a very strict constraint. The penalty contact allows for a little bit of numerical wiggle room, and it turns out that this wiggle room is very conducive to convergence, which is why I recommend the penalty method for most applications today in Abaqus standard. So just a summary of the direct enforcement versus penalty method. The big advantage of direct is the exact constraint enforcement. The disadvantage is the difficulty of obtaining a solution that can satisfy such a strict constraint. It turns out that the penalty method constraint is also pretty strict, but not not completely strict, and so it really helps the convergence. And it's also nice in the sense that you alleviate a lot of issues with over constraints. It's hard to do direct enforcement contact on a node which has lost its degrees of freedom due to some sort of kinematic constraint, like an MPC, say. All right. So a little bit on relative sliding. Some of you may have seen this animation before. The animation at the top shows you small sliding applied to a finite sliding application and the horribleness of that. These lines coming from the surface, if you can see those represent the tangent plane approximation coming from small sliding. And even though the contact is being enforced exactly correctly according to the small sliding algorithm, it's not appropriate for this application and you get a bad solution. So if you are in doubt, then you can use the finite sliding tracking algorithm, which is what you get by default with contact pairs, and it's what you get in general contact. If you have an application where you have surfaces being clamped together and they don't move around a lot, it's a large model and you want to have an efficient algorithm, you can try small sliding. But if you have any doubts, you can use this finite sliding algorithm. And if you want to use small sliding, you have to, add the small sliding option to your contact pair definition. All right. One note on the general contact domain. I think there's some misconception that general contact always means somehow contact on the entire exterior of a mesh. And that's one thing that you can do. You can do that in Abaqus Standard. You can do it in Abaqus Explicit. So that's the definition at the top. You can see the all exterior parameter here. But you don't have to do that. If you want to build a more efficient contact domain for your general contact, you can limit the contact inclusions to certain pairs of surfaces. And so you can build up a more efficient contact domain. In fact, the definition at the bottom is very analogous to defining a contact pair, if you want to look at it that way. Okay, so I was doing my disk through the ring problem with the contact pair, and I had issues with the edge sliding, so I quickly just changed star contact pair to these commands here with a text editor. It took a few minutes to do that, and then I was able to run that with general contact instead of the contact pair. All right. A little bit on the solutions that you get from contact analysis. We have here kind of a common occurrence where we have some body pushing down on another one. I've greatly exaggerated the deformation here, so this is more of a linear elastic application, so I've increased the deformation scale. And you might be surprised to learn that the stress at the edge of the contact is infinite according to the theory. And here's a demonstration of that. I took this handwritten notes here from my notes from elasticity when I took that as a graduate student. And you can see that as the radius that you're evaluating this pressure cube approaches A, you get infinite contact pressure there on the top surface. And if you try to simulate this with Abaqus, this is what you're going to produce. You're not going to get infinity, of course, but you're going to get higher and higher values for the stress as you make the mesh density smaller and smaller. So it's not uncommon to see strange things happen at the edge of contact, and there's really nothing I can do about that or anybody can do about that as far as I know. It's going to show up there because of this relationship to the, Abaqus is just doing a numerical process which is trying to produce, in this case, the linear elasticity solution is what it does. And just as a bit of trivia, if you think you can get away from problems like this by removing the contact and just using an applied pressure, well, then you're out of luck, because the same similar problem happens even when you put a constant pressure on the elastic's body instead of the contact from that punch. It's not so bad that you get an infinite stress there, but you do get a point where the stress is undefined. It just depends on how you approach that point as to what value of contact stress you're going to get, or stress from the pressure in this case. One thing about contact is the initial overclosure, the possibility that your contact might, by definition, be violating the contact constraints initially. And so you have to deal with that. So you really need to run data checks and look at your contact opening distance. That's the C open variable. And if you get negative values for C open, then you need to realize that that can cause a lot of problems in the first increment of your analysis. And so you need to deal with that. There are ways in general contact to initialize the contact state, to treat it as an interference fit. There are options to adjust the nodes strain-free to get rid of the interference, or to close a gap if you want to do that. Contact pairs also have similar options to adjust the surfaces, or to treat the interferences as some sort of press fit condition. But you do need to deal with this no matter what. So you just can't leave it there. I've gotten so many models over the years where it's just the only problem was that the contact was interfering in the beginning. Once you fix that, then the problems go away. All right, so strain-free adjustments. That's exactly what it sounds like. You just move the nodes to eliminate the gaps or the interferences or whatever is funny about the initial contact state. So you can find out the initial contact state again by doing the data checks and looking at the value of COPEN. Sometimes if you're doing contact pairs or general contact and you have commands in there to generate a press fit, then the C open might not be what you think it is. So it's best to do data checks without any commands that treat the interference as a press fit, and then look at your C open values and then decide what to do from there. Okay. All right, so that is a little bit on contact. Now I want to switch back again to some comments on Abaqus convergence. So instead of doing some sort of discussion of messages that you might get that indicate this or that, I'm just going to make some comments about some observations that I've made over the years related to Abaqus convergence. And I don't have to say Abaqus standard here, because the idea of convergence only applies to Abaqus standard, so it doesn't apply to Abaqus explicit, which you might think is great. I'll just switch to explicit, and I'll have a comment on that here in a minute. So how can I avoid an unfortunate outcome? That is, how can I avoid non-convergence or the abnormal termination of the Newton-Raphson method in Abaqus standard? Well, there's good news and there's bad news. Bad news is you can't avoid it completely. I've been building Abaqus standard models for a long time, and when I built my disk through the ring simulation, I had convergence issues. I was aware of the issues with the static stability, so I started out with implicit dynamics right away. I kind of took it out to generate that example. So I knew enough to do that, but I was caught up by the contact. So I just put in a contact pair and it got stuck. So I had to fix that. So no matter how many models you build, you always run into this eventually. Yeah, but if you have good modeling practices and you know what to do when things go wrong, then you can just overcome those. So I quickly saw that the nodes on the edge were getting flagged by the messages in the message file, and so I just knew that the edge contact was an issue, and I put in the edge in the general contact domain and was able to run that. But it's best to avoid convergence problems in the first place, which my comments are going to deal with that idea here. So first of all, avoid the simple mistakes. Most of the convergence problems are basic modeling mistakes. I just received a model today from someone who is pushing on a surface which is not in contact. So if you push on a surface which is not constrained and it's not in contact and you're using a force load, that's going to cause an issue. So in that case, you can switch to displacement controlled and avoid issues like that. But I consider that a basic modeling mistake. So some other simple modeling mistakes would be, missing boundary conditions, problems with the contact definitions. I left out some kinematic constraints, or I have conflicting kinematic constraints, or I have inconsistent units producing, wildly varying numbers in my calculation, which caused problems, or I built a bad mesh which might pass through a linear simulation but would not in a nonlinear simulation where, the change in the element shapes are taken into account, and so on. So you need to find these simple modeling mistakes by doing your data checks. Everybody makes mistakes. I make them all the time. But I do my data checks and I try to sort through those before I even get started. Once I do get a model that I think will produce a solution, then I'll try to run it like I did with my disk and the ring problem, and it'll come to a stop in some situations, and that's what happened to me. And I was able to see in one case that there was a problem with static equilibrium, so I switched to dynamics, and I saw in the second case that there was an issue with the edge contact, so I switched to general contact. But the partial solution that was being generated was very valuable to me to be able to make those changes. So look at your partial solutions and use your intuition and understanding of what is supposed to be happening and compare that to what is actually happening. You might be able to see how to change the model, to make things work. Comment number 2, don't use plane static analysis to simulate quasi-static motion. In this example, this is a similar situation to my disk through the ring example. I'm moving a shifter and I have a little rubber boot, and I'm doing a range of motion study to see what the boot does when I move the shifter. And right away you would expect to have problems with a static analysis to do a simulation, which is basically called a motion study. There is no true motion in a static simulation. The animation of a static solution may look dynamic, but that's just an illusion. You're just linking static equilibrium states together in a flip book kind of animation, and so there's no true motion there. If you want to get true motion, you have to do dynamic equilibrium. Sometimes we may try to compute motion and we don't even realize it. We might have a situation where everything is fine, and then we have a stick slip in the contact, or we have some sort of localized buckling, or some kind of contact wants to separate. And if you were doing a test of a real structure, what would happen is the structure would start to accelerate and move around. And of course, if you're doing static simulation, it's not possible for things to move around. It's static. So you have to take into account this quasi-static motion if you're doing those applications, and you have to do your static stabilize or your implicit dynamics, or you might even consider switching to Abaqus explicit if things get bad enough in terms of the convergence. If you're doing static stabilize, don't forget to check your energy. Don't forget to check your viscous forces. Don't forget to check your kinetic energy and your velocities if you're doing dynamics and you're trying to get quasi-static equilibrium. Understand and apply contact options correctly. Contact is a big source of issues. These are not really technical these days like they were in the past, but sort of self-inflicted by defining insufficient contact surfaces, or having unresolved initial penetrations, or using small sliding and finite sliding applications, or using direct enforcement when penalty enforcement will do. And it's really a problem to rely on contact for the constraints necessary for static equilibrium, because the contact state is part of the solution. So you need the solution to get the solution, which, as you can imagine, would cause issues. So don't be afraid to add some extra constraints. You might try contact control stabilize type command. I prefer to add constraints with spring elements or extra boundary conditions. You can always remove these extra constraints later as you get the structure to come into equilibrium with the contact. You need effective material modeling. So you want to be able to avoid issues with bad material modeling. So don't use linear elasticity for large elastic strain problems. Switch to hyperelasticity if you need to do that. There are issues with defining plastic hardening curves that come to an end. Abaqus doesn't extrapolate the hardening curve. It flattens out as perfectly plastic when you get to the end of a tabular definition. If you have irregular data, you might force Abaqus to try to follow a jagged hardening curve, which is an issue. So you can smooth out the irregular data. Remember that this may not be a convergence issue, but your isotropic hardening plasticity is not useful for cyclic loading. Okay, just wanted to make that comment. It's not really related to convergence, but hey, it's good to know. Unstable hyperelasticity is an issue, of course. And here's an example on the left of power law plasticity model. So this is nice. You can generate these kinds of models from handbook data. There's an entry on the learning community about how to do this, or get the plugin for doing it, or whatever. And so the nice thing about power law plasticity is it's a formula. There's no tabular data. The picture on the right shows a bad, in my opinion, hardening curve. Your hardening curve goes down when it should be going monotonically up. Otherwise, you're going to get convergence issues when you hit the down spot, potentially. Here's just an example of an unstable hyperelastic strain energy density. I'm stretching the material, that's lambda 1 and lambda 2, and I get less energy even though I stretched it more, which is not really reasonable. And so you want to avoid these unstable hyperelastic material models in the strain ranges of your application. Comment number 5, run the latest release. So here's an example of a model. I just ran this yesterday in Abaqus 2019. It takes a little while, but not too bad. But if I try to run this in Abaqus 614, it takes a long time. So the implication then is that the contact in Abaqus 2019, and it is issues with the contact there that are slowing it down in 614. So the 2019 contact is more robust, as you would expect, because Abaqus is under constant development. Comment number 6, convergence is user-defined to an extent. If you want to change the convergence checks in a limited way, you can do that. The keyword is star controls. The command you see at the bottom of this slide is a way to increase the number of cutbacks. That's relatively benign change. If you start going around changing the 0.005 for the residual check or whatever, then you might run into issues. One thing that's kind of common, I see this in some users' methodology, is to set a fixed residual check like you see on this slide. And this harkens back to the old days of Abaqus with the old p-tall parameter where the user had to define basically q tilde. Here, this command is overriding q tilde with a user-specified value of 0.01. And this is done because the corrections to the displacement are extremely small compared to the increments of displacement, but the residual force is stubbornly about the same magnitude as the average force. So when I take the ratio, I can't get a small number. So this bypasses that. You may want to consider modifying the model after you make this change to get rid of this need for this, but you might find that the solution that you produce this way is quite useful anyway. So just a warning for star controls. You can see that here if you change them. And comment number 7, avoid numerical ill conditioning where possible. So avoid things like thin shell element skins. You want to use hybrid elements for nearly incompressible materials. Abaqus actually forces you to do this, or to consciously override the error message that is generated if you try to use regular elements with nearly incompressible materials. Slender beams may need hybrid beam elements because of the big difference between the bending and the axial stiffness. And you want to avoid putting in floating point numbers into an Abaqus model that are out of the range of the understanding of the Abaqus code. Abaqus is not programmed to understand arbitrary floating point numbers. There's a range that it needs to use. Comment number 8, a model which is almost the same may run fine, so don't be afraid to make some small changes to try to get things to work. In this example here, I went in and pre-creased the surface, if you will, by moving the nodes over a little bit so that I was able to form a crease in this rubber component, whereas in the original model it was kind of couldn't decide what it wanted to do because of the the irregular deformation pattern from those quadratic tet elements. Now, of course, you have to decide for yourself if this small change is something that's reasonable to do, because small changes can cause large changes in other parts of the model in a nonlinear simulation. Comment number 9, know when to quit. So very few models may never be able to run in Abaqus Standard, or you might find that the features that you're using cause cutbacks to small increment sizes, which becomes inefficient in Abaqus Standard. So fortunately, Abaqus Standard models in a lot of cases can be converted easily to Abaqus Explicit. Abaqus Explicit doesn't have the Newton-Raphson method, and so your convergence problem would go away, and you would think your problem is solved, but then you'll find out that Abaqus Explicit has its own issues, which are topics for another day, so it's not a panacea. Finally, the last comment is that training is available. If you're interested in convergence in Abaqus Standard, there's a class called Obtaining a Converged Solution with Abaqus. There's a class on Contact in Abaqus Standard. There's now an official combined class. The actual name of it escapes me at the moment, but it's a combination of these two classes you can sign up for. And if you really want to investigate the use of Abaqus Explicit for very tough, challenging quasi-static simulations, or even for highly dynamic simulations if you have those applications, then you can look into signing up for Abaqus Explicit Advanced Topics. All right, so that takes me to the end in only a few minutes over time. So some next steps: watch for the email, which will have a link to a replay if you want to watch that. Of course, you can always go to the Simulia Learning community to search for things that you may not have seen already. If you want to sign up for a class, you can do that, and you can follow DS on social media if you're so inclined. So that takes us to the end. So what I'm going to do now is look and see if there are any questions and try to answer a few of those in the remaining time. Can you talk about symmetric versus unsymmetric solver? Yeah, so I didn't mention that, but what happens when you're doing contact modeling and you do the linearized structural stiffness, it turns out that that's a non-symmetric matrix equation, and if you're only storing the symmetric part of it, you may not be able to produce the required corrections. If you are using the symmetric solver, which considers the linearized stiffness to be symmetric, then if everything converges, then you're okay. So it's not you're not producing the wrong solution. But in some cases, you may need to use the unsymmetric solver. In fact, if you take the contact class, there is a slide in that class that talks about the recommendation for using the unsymmetric solver for contact models. So that's one of the first things that I try if someone sends me a contact model that's not converging and it's not using the unsymmetric solver. You just need to eliminate that technical fix before moving on to trying to fix the problem in some other way. Yeah, you can't. So the question, one question is about this idea of having infinite stress at some kind of a sharp corner. What would happen if you round off the edges? And I think you can avoid the infinite solutions if you have flexible bodies, but I'm not familiar with all the solutions for linear elastic contact situations. There are textbooks and references on contact mechanics where they talk about what happens in various cases And you can round off the edges. In fact, it's very difficult to produce solutions for sharp edges. And I always tell people that if you want to have an edge, you're going to have problems, and the best that you can do is round the corner to match the mesh density of the other side of the contact, so you can have a few elements conforming to the rounded off corner. If you want a sharper corner, then you have to build a finer mesh. How about dynamic implicit method to resolve convergence issues? Yes, that's I've started to use that more and more. And frankly, I prefer implicit dynamics with the application for quasi-static situation to star-static stabilized today. Star-static stabilized still has its uses, but I find myself more and more using the quasi-static implicit dynamics in lieu of static stabilized. I always thought that the slave should have more nodes. Why does the master need more nodes for contact? No, I'm not sure if I said that, but I shouldn't have. Or maybe it was in that picture, but the idea is that your slave surface would have the more refined mesh. So even in the sophisticated surface-to-surface algorithm, that is the recommendation. Now, if you're doing general contact, you sort of get, in a lot of instances, you get a balanced type of contact. It's not such a big issue for the advanced contact algorithms, but it is still a general recommendation that if you have a master-slave situation, that the slave would have a more refined mesh. And how much difference is there between quasi-static and static? There's a world of difference between static and quasi-static. Quasi-static, when I say that, I'm really referring to dynamic equilibrium. So in a dynamic simulation, you're allowed to have velocity, and it makes a world of difference to allow things to move. Even if your integration of the dynamics is kind of sloppy and imprecise, if you're not really interested in the dynamics, then that won't matter. But you're still allowed to have actual velocities being computed from the algorithms, and so that allows the simulation to deal with unconnected bodies moving around and things like that a static simulation just does not allow. So there is a big difference between doing a quasi-static simulation and doing a pure static simulation. And the question is, can we combine explicit and standard in 2 consecutive steps? The answer to that is not directly, but yes, you can do import. As long as the stuff you want to take from, say, standard into explicit, as long as it's compatible, you can do what amounts to a restart, basically, in the other code. There are limitations, of course, but you can read about those in the documentation. It is possible. Today in Abaqus, you cannot put implicit and explicit load steps in the same input file, say, but you can use this import to take, say, results from Abaqus standard into Abaqus explicit and so on. Next question is, can you talk about geometric correction and how it helps convergence? So that's a really good question. Abaqus general contact and Abaqus contact pairs with the surface-to-surface option allow the geometric smoothing of meshes in certain situations that you can read about in the documentation, and it is very helpful to convergence, and it's also helpful in the stress distributions that you get from the contact. It can help you smooth out high spots and so on and produce a nicer stress distribution. If you have large sliding contact, then it's not going to be helping that much. But if you have, say, press fit stress states and so on, then it is a great thing to do this geometric correction. Okay, let's see another question here. How can we find appropriate friction factors for different materials? I wish I could answer that question. I might get rich from that, but friction is very, very difficult phenomenon to model in a realistic way because it's all over the place. I teach a class on elastomers, and as part of the class, we do a fun exercise at the end where we try to, measure friction factors, and it's more like a party than a scientific experiment because it's kind of wacky. It gets, the factors are highly dependent on small details of how you're doing the test. And so unfortunately, there's nothing that Abaqus can do about that. And yeah, I don't have an easy answer for that except to say that, yeah, friction is problematic. Next question. Can you repeat what you said earlier about plastic hardening and cyclic loading? Yeah, what I was referring to is the difference between isotropic hardening plasticity and kinematic hardening plasticity. So the isotropic hardening, that's referring to the evolution of the hardening as you load the material, and it's a simplistic, isotropic hardening is a simplistic way of changing the yield surface, if you will, and it doesn't allow you to model known effects that are caused by cyclic loading. So you need to switch to cyclic loading plasticity models, and that by itself is a very large topic, which I can't get into today, but the terminology there is kinematic hardening. So if you're interested in this idea, you can look in references or do a Google search on kinematic hardening plasticity and find out more about that. Interference fits, there's really not a way to deal with those in Abaqus Explicit, which is the question here. The idea of doing an interference fit is coming from Abaqus Standard. Now you might try to do an installation or a sliding, assembly type analysis in Abaqus Explicit, which might be easier to do in Abaqus Explicit than Abaqus Standard. So I've got a time for a couple more. Edge to surface contact, is that solved better with explicit than standard? No, because there is no edge to surface contact in the general contact from Abaqus Explicit. There's edge to edge, but there's no edge to face contact in Abaqus Explicit. So unless you put in all of the edges, which is kind of a strange thing to do, but there's not the same kind of edge to face contact in explicit as you find in standard. Okay. Would it be a good approach for large contact models to relax the convergence criteria to get a partial solution, even if it's unreasonable, and so on? And the answer to that is, yeah, that's kind of a reasonable thing to do. If you're stuck running a model that only has like unsuccessful attempts, it's very hard to understand what you might, be facing. So anything that you can do to produce a partial solution, as long as you realize that you need to, go back and do the right thing eventually, as long as, as long as you understand what you're doing, yeah, that's a reasonable thing to do. I often do that myself. I'm doing that myself for someone. I'm putting in all kinds of controls, and this is because I can't really see what's going on yet. So I'm desperately trying to produce some partial solution to look at, and then I know to go back and, set things right when I want to do my final simulation after I find out what the problem is. Okay, one last question and then we'll wrap it up there. Negative eigenvalue is never related to contact error. That's an interesting question. I don't think that's true, but the negative eigenvalue messages they often appear. And someone told me one time that the limited negative eigenvalue messages are produced simply from an extrapolation process in Abaqus Standard Solution method. I don't know if that's true or not. Some a solver developer told me that one time. What you tend to see for problems with stability, static stability, is the sudden appearance of large numbers of negative eigenvalues. And so that's what you need to pay attention to. So it's quite possible in a contact model to see, negative eigenvalue messages here and there, but I don't normally associate that with the contact. So I don't know the exact answer to that question, but that's an interesting question. One last question, can you explain the all exterior and general contact? Yeah, that's simply saying that the general contact domain includes all of the free surfaces of all of the mesh parts that are in the simulation. So that's what all exterior means. So that sets up a very large, potentially general contact domain. And then in general contact, the idea is that you have contact of the domain with itself. Okay, so we're 1 minute past the time, so I'll end it there. And I don't know if there are any other final comments we need to make, but thanks to everybody for attending.
Thanks, everybody. And Like we mentioned before, it will be recorded, and you will receive notification on when that is available through our swim platform. So everyone have a happy holiday season and look forward to seeing you next time. Thank you.
Bye-bye, everybody.
Thanks, Randy.